We often marvel at the vastness of the cosmos. Galaxies collide, stars explode, and planets form over eons, but an equally fascinating world exists within the heart of every atom, the nucleus. Within this tiny space, protons and neutrons engage in a delicate dance governed by forces far stronger than gravity. Understanding these forces is key to unraveling the mysteries of the universe. Imagine trying to separate two magnets stuck together. You'd need to exert a certain amount of force to pull them apart. Similarly, separating a neutron or a proton from the nucleus requires energy. This energy, known as separation energy, provides a fundamental glimpse into the stability and structure of atomic nuclei. By studying separation energies, we gain insights into the forces that bind the nucleus together. These forces determine the energy released in nuclear reactions, the stability of elements, and even the processes that power stars. Consider an atom's nucleus, a tightly bound collection of protons and neutrons. Each particle plays a crucial role in the nucleus's overall stability. Neutron separation energy, S_n, refers to the energy needed to remove a neutron from the nucleus, leaving the number of protons unchanged. Proton separation energy, S_p, on the other hand, quantifies the energy required to extract a proton, leaving the neutron count untouched. These energies provide valuable information about the relative stability of nuclei with different numbers of neutrons and protons. For instance, a nucleus with a high neutron separation energy is more resistant to losing a neutron. Similarly, a high proton separation energy indicates a nucleus less likely to release a proton. These energies are not arbitrary, they are dictated by the complex interplay of forces within the nucleus. Scientists use specific formulas to calculate neutron and proton separation energies. The neutron separation energy, S_n, is determined using the following equation. S_n equals MaZ1 plus M_n minus MaZ times c squared. Here MaZ represents the mass of the nucleus with A nucleons, protons and neutrons, and Z protons. M_n is the mass of a neutron, and c is the speed of light. Similarly, the proton separation energy, S_p, is given by S_p equals MaZ1 plus M_p minus MaZ times c squared. In this case, M_p represents the mass of a proton. These formulas may seem daunting, but they simply reflect the conservation of energy. The energy required to separate a particle equals the difference in mass between the initial nucleus and the final products, converted to energy using Einstein's famous equation, E equals mc squared. By plugging in the known masses of nuclei and particles, physicists can calculate separation energies and gain insights into the forces at play within the nucleus. Separation energies are intimately linked to another important concept in nuclear physics: binding energy. Binding energy represents the total energy required to completely disassemble a nucleus into its individual protons and neutrons. In essence, it's a measure of the nucleus's stability. A high binding energy indicates a tightly bound, stable nucleus, while a low binding energy suggests a less stable configuration. The relationship between separation energy and binding energy is straightforward. The separation energy of a neutron or proton is directly related to the difference in binding energies between the initial and final nuclei. To accurately calculate binding energies, physicists rely on the semi-empirical mass formula. This formula takes into account various factors contributing to the binding energy, including the strong nuclear force, electrostatic repulsion between protons, and the surface and volume of the nucleus. By comparing experimental separation energies with theoretical predictions, physicists can refine their models of the nucleus and gain a deeper understanding of the fundamental forces that govern the universe. The journey into the heart of matter continues, and with each new discovery we unveil more secrets of the cosmos, from the smallest atom to the largest star.